Welcome. We're at the top of the hour. We will give everybody another 60 seconds or so to join, and then we'll kick things off. All right, I think we should get started. Welcome to today's webinar, SAS 201, an introduction to enterprise features. Before we get started, I just wanted to cover a couple of housekeeping items. The webinar today is scheduled for 50 minutes. We are expecting about 35 minutes of presentation material with the remaining time available for Q&A. If you do have any questions, go ahead and submit them via the chat box at any time, and then we will address them with the remaining time. If we don't get to your particular question, we will follow up via email within the next week. And you can download the PDF of today's presentation from the Attachments tab. My name is Rick Kutcipal. I'm part of the Product Marketing and Planning organization within the Data Center Solutions Group at Broadcom, and I am on the board of directors of the SCSI Trade Association. Joining me today is Tim Symons. Tim is an associate fellow at Microchip Technology and has been an active member of the T10 Technical Committee since 2005. Currently, Tim is the editor of the SAS protocol layer within T10. So today we're going to take a quick look at the SCSI Trade Association. We'll quickly follow that with a recap of last year's SAS 101 webinar, followed by a high-level description of the architecture of the SCSI protocol. Then I'll go into some of the evolutions in storage media and some of their usage models in today's ever-changing storage environment. And then Tim will take us into some of the fundamental features of SAS, focusing on some of the new ones specific to 24 gig, and then we'll wrap things up. So just a quick backgrounder on the SCSI Trade Association, or what we refer to as STAY. It's an organization that was formed well over 20 years ago by a handful of companies that developed and sold products based around a modern version of the SCSI command set, commonly known as Serial Attached SCSI, or SAS. STAY is the marketing arm of the ANSI T10 Technical Committee that is responsible for the development and publishing of the technical specifications for SAS. STAY then markets and promotes the use of SAS in traditional enterprise environments as well as modern data centers. And we welcome any additional companies to become members of STAY and help us contribute to the evolving use of SAS. For more information, I encourage you to go to the website at the bottom of the page, www.scsita.org/content. So I want to kick things off by recapping our SAS 101 webinar that took place about a year ago, where we introduced SAS as the serial incarnation of parallel SCSI, and that it is the foundation of a wide array of protocols ranging from fiber channel, USB, FireWire, and even InfiniBand. In the webinar, we discussed a pretty thorough evolution of SAS, beginning all the way back at SCSI 1 in the mid-'80s to Ultra 320 in the early 2000s to where we are today with 24 gig SAS. We also highlighted the flexibility of SAS as it spans the enterprise storage spectrum with products focused on server-based storage, external storage, as well as cloud storage. These products include HBAs, RAID cards, expanders, of course the cables and connectors, the test equipment, and a wide variety of targets ranging from SAS, HDDs and SSDs to SATA HDDs and SSDs. And remember, this is a long list of targets, including nearline drives, SMR drives, and multi-actuator drives. This was followed by some basic topologies of SAS, again, ranging from basic direct server attached storage to cloud and external storage. And then we wrapped it up with a discussion on a variety of data center applications and how they map to the overall picture. This is a great primer, and I encourage you to go take a look at it for a refresher. You can see it there on the Bright Talk link at the bottom of this slide. So with a basic understanding of SAS, we can take a little bit deeper look into the makeup of SAS. And we find this pretty interesting. And the SAS specification is broken into layers, which are developed and published independently. The physical layer, denoted by SAS, specifies the functional requirements for the serial attached SCSI physical interconnect. So this on a device is typically the PHY layer and a good portion of the wrapper, depending on how it's implemented. It's important to note that all SAS physical layers are definitely compatible with the Serial ATA physical interconnect specification. The SAS protocol layer, or SPL, defines the rules for exchanging information between different SCSI devices using a serial interconnect. This is the layer that connects SCSI to the SAS serial interface. So this is the layer, right, that connects all of the rest of SCSI then to that physical layer. So this is definitely unique to SAS. This layer was separated from the physical layer in 12 gigabit per second SAS to give more flexibility in implementing features on the protocol side, make them independent of the physical layer. The SCSI command layer is a collection of specifications specific to SCSI itself. So the green boxes are really the foundation of SCSI. And so instead of digging way into these, I thought I could give just a high-level definition of each one, just to make you familiar with what they are and as they come up in different pieces of the standard. So SPC, or the SCSI primary commands, they're the ones that define the SCSI commands that are mandatory and optional for all SCSI devices. So that's really the heart of SCSI right there. Then there's the SCSI block commands, or SBC. These are the commands that these are the command set extensions that facilitate operation of SCSI direct attached block devices. So these are the ones that are integral for using SCSI in a storage environment. The SCSI architectural model, or SAM, is the specification that defines a reference model that calls out the common behaviors for all SCSI devices. And then there's SES, or SCSI Enclosure Services, and these document the commands and parameters necessary to manage non-SCSI elements installed in enclosure. Example, in a Gbaud, there might be fans, power supply, all to be monitored and give feedback to. And it should be noted, that SES is the fundamental management infrastructure that's inherent in SAS. And then there's the SCSI to ATA translation specification, or SAT, that defines the protocol requirements to bridge between SCSI and ATA devices, allowing for SCSI components to interoperate with ATA devices like SATA drives, whether they're HDDs or SSDs. Then there's another group of specifications focused on zone block commands, or the ZBC commands. This specification defines a model and command set extensions to facilitate the operation of zone block devices. Zone block devices would include like SMR drives. Note that it's SAS3 and SPL2 that make up the fundamental building blocks of 12 gigabit per second. And it's SAS4 and SPL4 are those that make up the 24 gig SAS specification. Next, I want to talk a little bit about some of the advancements in storage media to address two fundamental goals. One, higher performance, and then two, higher capacity. Everyone's aware of the enormous investments in solid-state storage in the recent past with things like new bit cell architectures to improve capacity, innovations to improve endurance, etc. But you can't overlook the work that's been done on the hard disk drive side as well to address very similar issues. In fact, SAS has been very well positioned to either implement or enable most of these features. So I've created a table listing some of these and SAS's roles in these technologies. So I started out with some of the magnetic recording technologies, so TDMR, two-dimensional magnetic recording, focuses specifically on faster write performance. And then the assisted magnetic recordings with hammer and mammer, two variants of a very similar thing, very focused on increases in capacity. Then there are the SMR flavors with SMR and hybrid SMR, supporting shingled magnetic recording, and then variants thereof. Again, both HDD technologies optimizing for capacity. And these are implemented, as I mentioned a moment ago, by ZBC and ZBC2 command sets. Then there's multi-link SAS. This one is not specific to the media itself, but more focused on the performance, mainly around SSDs can take advantage of it. And this is something that's native to SAS, and that's wide port connectivity. So supporting a drive with more than one PHY, maybe two, maybe four PHYs, and ganging those PHYs to increase the performance. And we're seeing a number of drives, coming out with that on it today. Then there's multi-actuator. This is kind of a buzzword. You see a lot of it in the media. Definitely an HDD technology focused on performance, but a relatively unique type of performance, more around IOPS per terabyte than raw bandwidth. And SAS supports this with native multi-LUN connection support. And then finally, storage intelligence. And storage intelligence is a catch-all bucket that we have termed that is focusing on SSD performance. Things like background garbage collection, streaming capacities, things like that, optimized for SSDs. In the SAS 101 webinar, we talked a little bit about the different applications for SAS. In this webinar, I wanted to expand on that and talk about some of the trends that are taking place within the storage ecosystem. SAS is very flexible in its possible deployments, supporting a range of media connectivity with the different SAS and SATA drives. And at its inception, this flexibility, specific to SAS and SATA HDDs at the time, made it the perfect fit for direct connect server architectures all the way up to very large storage arrays. Today, storage requirements and the use models are changing, and they're changing drastically. Take, for instance, the Internet of Things, where things like doorbells, thermostats, refrigerators, individual light fixtures are all connected to the Internet, creating enormous amounts of data. So data point, in 2018, there were approximately 7 billion devices connected to the Internet. And in 2025, IDC estimates that there will be more than 41 billion devices generating a staggering 80 zettabytes of data annually. Now, these are very staggering numbers. Another example is the explosion in social media, where every family video and photo are posted to Facebook and Instagram. Every tutorial or experiment is posted to YouTube, and every dance move is posted to TikTok. Who would have thunk, right? As of this year, an estimated 500 hours of video is uploaded to YouTube every minute. That's a lot. And on average, 1 million TikTok videos are watched every day. These are just two high-level examples driving changes in the storage requirements, but both of these can be used to illustrate modern demands on the storage infrastructure. As I mentioned, these use models create massive amounts of data, and that this data has very fundamental different characteristics and drive very different storage requirements. A fraction of this data will be accessed frequently and require very high performance path. This would be considered hot data. Architectures dedicated to hot tiers are focused on performance, with drives typically directly connected to the compute node and have a very limited amount of capacity, or very limited number of drives. An example of a hot tier application might be on your favorite shopping website. When you're searching for a product, it's very important for that service to supply the results very quickly. You click on something, you want to see it, and you want to keep shopping. There's other data that will be created and accessed a few times and must remain accessible. This is termed warm data. This tier will balance the need for performance and capacity. And dollars per gigabyte start becoming a significant variable in this overall equation. A variety of architectures could be used for this type of storage. One example would be a compute node, say, connected to a cascade of leveraging SAS expanders with nearline SAS drives, just as an example. Scalability is an important attribute of these systems, and SAS natively enables hot add of additional storage by simply cabling another Gbaud to the array. An application example might be using the same shopping website that I used a moment ago. You find that item you're looking for, but you want to look at the 2 megabyte user's manual. This data is occasionally accessed and takes a little longer to come up. And finally, there's some data that will be archived and almost never used, and this would be termed cold data. This tier is all about dollars per gigabyte, so the most cost-effective media has to be used and is almost always some form of SAS or SATA HDDs and could exceed hundreds of drives in a single topology. In my example, I show a compute node connected to a cascade of Gbauds, again using SAS expanders with SATA or possibly SATA SMR HDDs to optimize for that cost per gigabyte. Again, using my shopping example, things like your order history and things like that are rarely or never, but need to be saved, would be stored in a cold tier like this. All of these examples rely on SAS connectivity and would deploy a common management infrastructure. And that's really important, especially in these large data center deployments, that there's a common management infrastructure that's built into the overall protocol. And with that, I will turn it over to Tim. Tim?
Thank you, Rick. Can you hear me okay?
Yes, I can.
Okay, thanks. Yep, so just a reminder, my name's Tim Symons. I'm an Associate Technical Fellow at Microchip, and we'll be looking in the next few slides to highlight some of the technical aspects of 24 gigabit SAS and how we achieved doubling from 12 gig, how that technology was achieved. So in the slide in front of you, you'll see the red chevrons, and they equate to new PHY enhancements implemented to accommodate doubling of the bit rate for each lane. The blue side, that's protocol enhancements, so block functions that improve efficiency in large-scale SAS systems. So we've got the electricals and the protocols in the two sides. We're going to take a little bit more detailed look at the two of the PHY enhancements, one for forward error correction and the other one for transmitter and receiver training and tuning in the next few slides. So just staying with this one for a moment, on the protocol and block side, the fairness updates help to improve performance within the SAS fabrics. Fairness can become unbalanced in very large topologies where devices are further away from the host, tend to not get their fair share of bandwidth. So the protocol has been modified to ensure that balance is retained. And this is very important in the 24 gig infrastructure, where we're sometimes dealing with 6 gigabit per second SATA drives, as well as 12 gig SAS drives, as well as 24 gig SSD drives, all cohabiting within the same SAS ecosystem. So different performance levels of devices, and we don't want to starve any of them. As Rick mentioned, this storage intelligence also has been added or enhanced for SSDs, solid-state drives. And essentially this translates into improved SSD efficiency and balance of bandwidth towards those devices. For very large topologies, management, well, in all topologies, management's important, but as the scalar topologies increase, more and more devices need to be managed. So the SAS management protocol, SMP, priorities have been modified as well, again, to help with very large infrastructures. So SAS 24 gig delivers higher IOPS and higher bandwidth than we had before and in previous generations. And that's really just as technology evolves. We got, if we look at where SAS 24 gig fits in the ecosystem, a SCSI controller plugs into a server, and that talks to a PCI bus. And SAS 24 gig is 50% higher bandwidth per lane than PCI Gen 4. And it's only 30% slower than PCI Gen 5. So 24 gig SAS is really the current generation for the current infrastructure and interconnect system. Nice, there we go. So what are the challenges of 24 gigs, going to 24 gig and doubling the line rate? It's not trivial. When we looked at moving to 24 gigabits per second or 24 gig SAS, we wanted to ensure that we retain backwards compatibility with the existing ecosystem and infrastructure. So I want to make sure I can still build multiple rack systems, rack-to-rack systems. I want to have a backplane in a rack so that I can support a lot of disk drives within one chassis. So that's a backplane environment. And I need to, so at 24 gig, I still need to better support those. And that's quite challenging at these bit rates. And the primary challenge is signal integrity, electrical signal integrity. What happens as you increase the frequency is the emissions from adjacent transmitters and adjacent PCB traces can actually interfere with each other. And this effectively creates noise on the channel and reduces your signal-to-noise ratio, resulting in data bits getting corrupted or reversed. Perhaps to put this into a more digestible context, if you're in a railway station, a high-speed train goes through, you really feel that rush. It almost sucks you towards the train, just a wind rush of that train. That high performance is disrupting you on the station, whereas a slow train goes through, you don't feel anything. So analogy anyway. So if we look at those bit error corruptions, as we move to 24 gigabits per second, the effect of the corruptions are we end up with 1e to the minus 9. So that's one error or one bit gets corrupted every billion bits that are transmitted. Yeah? Doesn't sound a lot. However, that equates to 22.5 errors a second. So for each of those errors, you'd have to do a retry if you weren't able to correct it. A retry generally means the whole transaction has to be retried, not just that one packet. So it's more disruptive than just resending the same bits over again. It's a whole transfer often has to be retransmitted. In previous generations of SAS, we've achieved a one error every 1e to the 15. So that's 15 zeros on the end. And so we wanted to retain that at 24 gig. So we needed to add some technology to do that. But again, back to context, one error every 10 to the 15 bits is one error retry every 12 hours and 20 minutes. So better than 22 a second, one every 12 hours, 20 minutes. That's a good error rate to aim for. And so we want to achieve that at 24 gig. All errors are detectable in SAS. There's a CRC checker, and so no false data is ever recorded. However, just those retries, as I mentioned earlier, can be quite disruptive to the overall system throughput. So how did we solve these challenges? What features went into the technology to solve them? So one of the technologies is transmitters and receivers exchange messages so that the transmitted signal, the shape can be modified to align with the amount of reflections and noise in the room or in the cable. One example of that would be, again, taking it into a real world. You'll notice at the beginning of this presentation, I asked Rick if he could hear me okay, and Rick responded, yeah, he could. That's me using my voice, my outside voice, or my voice suitable for this call. And you do this yourself naturally using your inside voice or your outside voice, depending on the environment. So it's a common feature that we all naturally do. We're just now doing this in electronic devices and transmitters and receivers. The second thing we did was adding error correction. So you noticed earlier we talked about one error every 1 billion bits was unacceptable. And so there's a technology, forward error correction, and what that does, it adds a complex checksum onto the transmitted data, and using that checksum, an algorithm called forward error correction can go back, find out where a bit has been corrupted, knows its location, and can actually correct it. I sometimes like to say to this is, it's like adding subtitles to your presentation. People may not catch every word, but they can read the subtitles and they can catch up. So in order to support forward error correction, you need to transmit a constant size block of information. And so for 24 gig SAS, we actually changed to transmitting packets of equal length and then adding an error correction field onto the end of that. So we'll look a little bit more at that in the next slide. So forward error correction. So SAS uses Reed-Solomon error correction algorithm. This algorithm, there are different types and have different characteristics, but the Reed-Solomon correction has good characteristics to match with the way that SAS works. Coincidentally, the same algorithm, algorithm is used in Ethernet. Ethernet has a slightly different set of requirements. They use very large packets, and that topology is allowed to drop packets as well. So they can have stuff arrive in and out of order, and it doesn't disrupt the transmission very much. So the size of their packets is 544 symbols, and then each symbol contains 10 bits. So that's 5,400 bits per packet. And in order to decode or correct, you have to receive the entire 5,440 bits, and then an arithmetic process is carried out on those 540 bits to work out if there are any bit errors, where they were, and to correct them. And on a packet that size, allowing for, once you've got to buffer the data and then you execute the algorithm, is roughly 100 nanoseconds delay or time to do that process before you can successfully say this data has been corrected and you can forward it to the egress port. Those times, that delay time is way too invasive for SAS. And so although we use the same algorithm, we use very different size packets. SAS uses Reed-Solomon code, and then in the brackets here you'll see 30, 26, 5. 30 is the entire packet length in symbols, so it's 30 symbols. 26 is the actual payload. Of those 30, 26 of those symbols are payload. And then 5 is the size of each symbol. So you can see we get to a total of 130 bits of payload and 150 bits of total information in each packet. The nice thing about having a packet that small is we can buffer it very quickly. Working at 24 gigabits per second, we buffer it in a very short period of time. The algorithm is working on only 150 bits of information, and it takes about 4 nanoseconds to process that. That time is faster than it takes us to receive the next packet in line. So we're not impacting the run rate of a channel. We're just adding a little latency before it gets past the egress side. And 4 nanoseconds is not disruptive to these SAS channels. By adding forward error correction, we're able to increase our error rate by 1 million times. And that's, again, worth reiterating. That takes us from 22 errors every second to 1 error every 12 hours and 20 minutes. And for SAS or any sequential transaction, you get a bit error. You can't just send that bit again. You have to send the entire transaction again to get it corrected. So the other technology I wanted to deep dive into, this is second of two, was active PHY transmitter tuning. So going back to the analogy, I asked Rick, could he hear me? And I would have adjusted, or adjust the microphone or adjust my voice levels to match that. We do that again. We do that also with the electrical signaling in a system. So we did this in SAS 3 actually at Power Up. You switch on your host and your disk drives, and the links would negotiate with each other. Can you hear me? How loud do I need to talk? One of the disadvantages of that, or one of the problems we found up over time, was the system is usually cold at that point in time. The disk drives are not spinning prior to you doing the first link up. Your GPUs aren't executing code. Your processors aren't executing code. And we find that over the next few minutes, the system actually gets warm, gets to a different temperature than the one we negotiated at. And temperature is one of the factors that impact dielectric and silicon receiver parameters. And so we find it sometimes drifts a little bit off its optimal settings. So for 24 gig SAS, we added an additional set of codes that said while data is being exchanged, we can add in a negotiation between the transmitter and receiver. The receiver can drop in a small code that says, I need you to increase amplitude. Speak a bit louder, I can't hear you anymore, or change the pre-emphasis or change the de-emphasis because I'm losing a little bit of signal. And so that way, while data is being passed, the signal can change its characteristics. Another analogy of this is, you're in a large building, let's say an airport concourse, and the announcement, if the announcer's microphone the speakers are not tuned for noise cancellation to match the building, you can barely hear what the announcer has said. Whereas a properly tuned system using modern speaker systems will have echo cancellation that match the building, and you can generally hear pretty clearly what they're saying. It doesn't stop you missing your flight, but you can hear it. So the combination of these two technologies, transmitter tuning and forward error corrections, allow 24 gig SAS to support cables up to 6 meters and backplanes up to 18 inches traces using non-exotic materials. So we're not requiring you to use very expensive materials to do this, and so that was another goal for ensuring that the SAS ecosystem would remain as it has been in previous generations. So just to summarize this section, we've doubled the bandwidth per lane. Systems can use multiple lanes per device, and that's Rick alluded to that in multi-link end devices. So 24 gig is only one lane on one of many, so you can see the bandwidth is quite high on these systems. We've ensured we can build systems the same as we used to, so we can have 6 meter cables that allows us to go rack to rack very easily. Backplanes we can daisy chain through multiple Gbauds. And the enhancements also allow us enough budget that we don't have to use the most exotic, most expensive PCB materials and connectors that you have that you would have to do, in other words, if we didn't have these features. We tweaked the protocol to support larger systems and technology devices of mixed types, and that's done to ensure fairness and avoid starvation when you have a storage system built up of maybe different technologies that operate at different speeds, or just literally the scale of the system as you cascade further and further away from the controller. The fairness needs to be balanced for all devices in that system. 24 gig SAS intersects very well with PCI Gen 4 and Gen 5. The bandwidth of the host can actually keep up with the SCSI interface and truly saturate 24 gig bandwidth that's available there. So finally, the SCSI Trade Association, we do interoperability tests, and we've already hosted one plug fest to verify 24 gig SAS ecosystem, and with more to follow. With that, I'll hand over back to Rick for final words and Q&A.
Great. Thanks, Tim. All right. In conclusion, I'm hoping that you found this webinar useful while we dug a little bit deeper into SAS on things like the high-level architecture definition of SAS, the fact that it's made up of independent layers for optimum flexibility, realizing that there are continuously changing demands on storage, and I use the two examples of Internet of Things and social media, and the fact that the flexibility and scalability of SAS are very well suited to meet these particular demands. And then finally, like just what Tim was discussing, that T10 has been focusing on very specific innovations and features like forward error correction, like continuous adaptation, or the real name active PHY transmitter adjustment, in order to maintain the robustness and reliability of SAS moving into 24 gig. And with that, let's look at some of the questions. So I do have a number of questions here for some combination of Tim and myself. The first one, do you have attachments in the presentation to share? Yeah, and I think I mentioned that in a PowerPoint, or excuse me, a PDF of the presentation should be linked to on the attachments tab. It says attachments and links. It should be listed in there, and you can download it. If you can't, you can, we can follow up with you. But that should be available right now on that link. All right. So the next one, Tim, I think this one's for you. Could you explain a little bit more about the need for forward error correction?
Yeah. So at 12 gigabits a second and previous generations, 6 and earlier, the noise characteristics of a transmitter to a receiver and also transmissions through a PCB were more affected by crosstalk and reflections. Whereas as we go up in the higher frequency ranges of 24 gig, we do get more disruption to the channel. And so the real need for it was, if we didn't have forward error correction, we would halve or even go down to 1/3 the length of cables and 1/3 the length of PCB traces. We'd also have to require quite exotic materials, Megtron 10 and beyond, and also we'd probably have to change our connector interconnect to all the disk drives as well to support 24 gig. So it would have been quite a disruption. So we needed a technology that could give us the data integrity and data delivery of valid, uncorrupted data. And so that's why we turned to forward error correction. It's been proven in other technologies. Ethernet's had it for quite a while. So we weren't reinventing the wheel, but what we were taking a concept that successfully being used in other technologies and applying it to SAS. So we were able to keep the latency low, channel costs down, and we were able to continue to support the same ecosystem requirements of 6-meter cables and backplanes as we were. So Hopefully that addresses the question. A little bit repetitive of what I said, but hopefully that addresses the question.
Good, thanks. So the next one, how do you see 24 gig SAS and by 4 and NVMe Gen 5 drives coexisting? You wanna take that one, Tim, or you want me to?
Yeah, well, let's both have a go at it. I think if I speak from the 24 gig side and a rate that, as Rick mentioned, disk drives themselves can have multi-links on them. And so the by 4 nature of an NVMe by 4, that just gives it more bandwidth on a Gen 5 system. So Gen 5 reading 32 gigabits per second on NVMe. Whereas SAS, we're looking at 24 gigabits per second. It's quite reasonable technically to add by 4 links to that. So the technology and the bandwidth is pretty similar between the two. Rick, I don't know if you want to add to that.
Yeah. So the one thing that Tim just went through was some of the investments and improvements that we have made in 24 gig SAS to account for these higher data rates, right? And so there will be a difference in the reliability of those particular devices. In general, they will coexist. Probably target at slightly different, market spaces, if you will. Okay. Next one, Tim. In large Gen 2 or Gen 3 domains, I'm assuming SAS domains, the end devices can suffer with response time issues due to retiming delays introduced by the expanders in the past. Is Gen 4 looking at ways to reduce these delays?
Yeah, that's a great question about fairness enhancements. So this observation is that as you add an expander, and if you daisy chain to another expander, another one, what happens is when a transaction's finished, the host says, I've finished this transaction. The first device, the first expander within that tells all its attached devices, hey, you've got some available bandwidth. And what can happen in a very heavily loaded, congested system is that the devices closest to the host get serviced first. So what we did in SAS 4 and SPL 4 specifically and beyond was add in fairness enhancements such that you don't just say a device is waiting for available bandwidth or available transaction. Each request comes with an age, and so that ensures that it doesn't matter where you are in that infrastructure, you will get a fair crack at getting bandwidth as it frees up. So that is a change from Gen 3 and Gen 4. And it becomes more prevalent as you go to higher performance because you're attaching more devices and you're sharing that bandwidth between more devices. So we're seeing it become more impactful at that rate.
Okay. Thanks, Tim. The next one, what is the outlook for HDDs given the ongoing acceptance of SSDs in the enterprise? So I can take it, and Tim, if you have comments, you can have a crack at it as well. So I did talk in my section. I did talk a lot about HDDs, and the SSDs are gaining quite a bit of market share. However, there are different needs, and in my examples, I showed those warm tiers and those cold tiers of storage, and how important dollar per gigabyte is in those particular applications. And that's all serviced by HDDs today. And for the foreseeable futures, with a lot of those innovations that we talked about on the following slide, a lot of those were optimizing for capacity. And so right now there still is a sizable gap between the dollar per gigabyte on, equivalent SSDs or compared to HDDs. Will it always be that way? Probably not. But for the foreseeable futures, HDDs are going to play a very important role in enterprise storage. Tim, anything?
Yeah, just a little comment, really. Comparison HDDs, SSD. We talked about warm storage, cold storage, and intermediate and hot storage. For rotating media, that's at one performance level. For SSDs, it's a slightly different performance level, and this is why we're seeing NVMe work hand in hand with SAS. They don't replace each other. They have different performance characteristics, and they work hand in hand with each other. So it's part of that. This drives us still by a long way the best cost per gigabyte of storage, or cost per terabyte of storage, and so in large cold storage systems, that's required.
Okay. Another one, in terms of scalability, how large of a topology is possible? So I can take that one, right? So SAS, SCSI itself, it could be, I don't know, it's what, 64K or something. It's some unreasonable number. More realistic, practical cases are being limited by the route table in the expanders. And so that's on the order of thousands. Practical, true practical applications, we're seeing it at about, 1,000, maybe just north of 1,000 connected devices. So Tim, any comments on that?
No, totally agree. You may break your network into segments so you have total accessibility to tens of thousands of drives, but you really only want hundreds to up to 1,000 per regional zone, just to keep your bandwidth balanced.
Okay. Next one, can you comment on the performance implications of SMR? So I did talk about SMR and what we're doing in T10 to support it with the zone block commands, etc. And in the press, SMR has gotten a significant feedback on performance, but the important part is you have to understand the type of SMR that's being used. In the enterprise, it's all host managed SMR. So that means the higher levels, manage the zone allocations and the streaming of data to make sure that you're dealing with the shingles, the overlapping tracks correctly. In drive managed SMR, all that is handled in the drive, and that can have performance implication, but that technology is not used in the enterprise. Tim, anything?
No, good answer. Thanks.
Yeah. Do you think 24 gig will be applicable to SSDs and HDDs? And HDDs will remain 12 gigabit per second. Right now, HDDs surely can't take advantage of the bandwidth that's available in 24 gig. And right now, it does seem to be focused, the technology itself is focused on the backbone and then SSD connectivity. So right now, that's the way we see it shaping up. Tim, anything?
Yeah, and I think if we go back about 8 years or so, someone asked me the same when we went from 3 gig to 6 gig, and the platters don't get data off that quickly. Well, look where we are. So
right, true. Yeah. All right. Okay, how does SAS4 deal with the higher value AC block capacitor specified in U.3?
Yeah, it's just really getting into the details. Yeah. So U.3 allows you to interconnect SAS devices and PCI devices in a similar backplane environment. And AC coupling, all devices, all SAS devices are AC coupled, so you got a capacitor that sits between the transmitter and the receiver. The value is different between different technologies. However, what we did for SAS and is common for a lot of receivers, we changed the blocking, the AC capacitor values, derated them. This does not have a very significant effect on the signal, and so we were able to accommodate multiple technologies changing the AC capacitor value without having significant change in the error correction. So if you have a look at the U.3 specification, you'll see a slightly different capacitor values than specified in the SAS environment. However, that has been endorsed by SAS and it does not have any impact on it.
Okay. Perfect. Thanks. And I think the last one, to achieve 18-inch trace on backplane with a 6-meter cable, what budget was assigned to the host adapter? Yeah,
in SAS, we don't assign particular budgets to particular parts of the subsystem. You'll find perhaps in the back of the SAS specification an example in the appendix. I think that they sort of call out, well, what if we had 4 dB loss in the disk drive and 2.5 to 3 dB loss on the host before we got to the cable. But those are just examples; they're not requirements. Essentially, the channel end-to-end from transmitter to receiver is a 30 dB loss channel, and how you use that is really up to you. You know, sometimes when your disk drive is very close to your host, you may actually choose to use that budget in perhaps a lower cost material, and you'll have a 30 dB loss channel in a 12-inch connection. So SAS is very flexible in that nature. And so we don't assign specific budget to any specific portion of the channel.
Okay. All right. Thanks, Tim. And it looks like that's all the questions we have received. Thank you for your time. If you haven't rated this, please go to the Rate This tab. You can rate the webcast and also provide feedback. And thank you for your time.